Hello everyone, very good evening. Today we will be talking about the reciprocating air compressor. So this is the 12th live session and the final live session in this series for this course Applied Thermodynamics. So let's start this session. So very first, to introduce with the compressors, what is a compressor? What is a compressor? So compressor is a mechanical device that imparts the mechanical energy to a fluid, or in the case of compressor, it is the fluid is a gas. So compressors are mechanical devices that uh, you know that increase the pressure of gas uh, by the application of mechanical energy, and meanwhile it will reduce the volume as well as increase the density. Okay, so compressors are basically mechanical device that increase the pressure of a gas, also decrease the volume and increase the density at the expense of mechanical energy. Okay. So compressors are basically used for gases. So what happens in the case of liquid? So for the same purpose, in the case of liquids, for the same purpose, the pumps are used. So pumps are basically used to increase the pressure of liquids, but there is no significant change in volume and density. Okay, so the basic difference between the pumps and compressors is the pumps are used for liquids. They increase the pressure of liquid. There is no significant change in the volume and density, and they are mainly used to pressurize the liquid and transport it. But in the case of compressor, they are used for gases. Significant changes there in the volume and density, and they are mainly used uh, to pressurize the gas and change its density. Okay, so these are the main differences between the compressor and pumps. Basically, pumps used for liquids and compressor for gases. Now, what are the different types of compressors? So basically compressors are divided into two parts. The first one is the positive displacement compressors, and the second one is the dynamic compressors. So in the case of positive displacement compressors, yeah, the positive displacement compressors are uh, you know in these type of compressor the flow is intermittent. Okay, and in the case of dynamic compressor the flow is continuous. And also in the case of positive displacement compressor, the compression happens uh, due to the trapping of air in the reducing space. So in the case of piston cylinder arrangement, uh, the air is inside the cylinder, and then the piston goes up, so the space is reducing, and this reducing space results in the compression of the gas. But in the case of dynamic compressors, the compression happens because of the transfer of kinetic energy from the rotor to the gas, and this transfer of kinetic energy results in the pressure change in pressure of the gas. Okay, also these positive displacement compressors again are of different type. So reciprocating and rotary compressors are there. Reciprocating means the motion of the piston inside the cylinder is reciprocating. Again, they are of different type: single acting, double acting. If the fluid is one side of the piston, it is single acting, but if the fluid is on both side of the piston, that is called as double acting compressors. Similarly, the diaphragm compression, and in the case of rotary compressors as well. So the positive displacement compressors are divided into two parts: the rotary compressor and reciprocating compressor. They are basically the principle of air compression is by trapping the air in reducing space. And for the dynamic compressors, the principle is compression of gases by the transfer of kinetic energy to the gas by the rotor. Okay, so these are the yeah, so these are the basic type of compressor, different type of compressor. Also, in the case of positive displacement compressors, the rotary compressors are used for low quantity. No, sorry. This is yeah, this is wrong here. So the rotary compressors are used for high quantity at low pressures, and the reciprocating compressors are used for low quantity at high pressure. Okay, so rotary at high quantity and low pressure, and reciprocating are low quantity at high pressure. Okay, so this is basically the classification of the compressors. Now as the title suggests as well, so our focus in this chapter is on reciprocating air compressors. Okay, yeah. So in the next few slides we will talk about reciprocating air compressors. So very first, uh, how the air compression happens, what are the different processes to compress the air. So basically air compression can be uh, happen by processes like polytropic process or isothermal process or reversible adiabatic process. All these processes are there. So you can see these three processes: isothermal, reversible adiabatic and polytropic processes on this left figure. And also this hashed area shows the work done in the compression for different processes. Okay, so from this figure you can see the minimum work is done for this curve, that is PV barabar PV is equal to constant. That means this is isothermal curve, right? So reversible isothermal compression results in the minimum work done. Similarly, this PV raised to power gamma is equal to constant. This is a reversible adiabatic process, and this reversible adiabatic process results in the maximum work done on the gas for compression. Okay, so basically the work done. So basically, the compression work done is given by this formula. The work done is equal to minus VdP for the, for uh, machines. There is a steady flow. So the work done on the compression is given by minus VdP. So when we solve this uh, work done equation, we got this formula for reversible polytropic process, that is Wn is equal to n by n minus 1 P1 V1 into P2 by P1 raised to power n minus 1 by n minus 1. Okay, so similarly the formula for adiabatic process is the n is replaced by gamma, and also the reversible isothermal processes, the work done is P1 V1 ln P2 by P1. Okay, so as this figure suggests, the minimum work done for compression is in reversible isothermal process, and the maximum work done is in the case of adiabatic, uh, reversible adiabatic process. Okay, so the similar thing is mentioned here as well, that minimum compression work is done in reversible isothermal process, and the maximum compression work is done in reversible adiabatic processes. Okay, so whenever a reciprocating compressor works, there is some heat transfer always. So the reciprocating air compressors definitely the work done is lower than this reversible adiabatic process, but the minimum work done can be achieved only if we use intercoolers between the stages in the case of reciprocating air compressors. Okay, and also in the high rpm compressors where there's no time for heat transfer, so they are basically very close to the adiabatic compression, reversible adiabatic compression, and the work done is the maximum work done there. Okay, And in the case of reversible adiabatic processes, uh, for the compression process, the work done is calculated by the change in enthalpy, the H2 minus H1. Okay, so here the work done W can be calculated at H2 minus H1. Okay, the change in enthalpy. Okay, so now if we talk about the reciprocating air compressors, so here you see in this figure, the reciprocating air compressors are that piston and cylinder arrangement here, but this reciprocating air compressors work on the two stroke. The first stroke is the suction stroke, and the second one is the compression stroke. Okay, so the typical indicator diagram you can see in this middle figure. Okay, so when the cylinder is at top dead center and it starts moving downwards direction, so the air present in the clearance volume start expanding. It expands up to point B here. Okay, it expands to point B here, and then the pressure in the cylinder goes below the atmospheric pressure and the inlet valve opens, and the air gets sucked into the cylinder from this point B to C. Okay, so once the air is sucked into the cylinder and the direction of the piston changes, the piston starts moving upward in upward direction, and it starts to compress the air inside the cylinder, and the pressure start rising from point C to D. Okay, and uh, at some point D, when the pressure inside the cylinder is higher than the pressure in the storage or the discharge pressure, the outlet valves opens and the compressed air gets you know it starts discharging into the storage cylinder. Okay, and then similarly, uh, the cylinder reaches the top dead center and the second cycle starts. Okay, so basically the reciprocating air compressors are two stroke, works in two stroke. The first one is the suction stroke, and the inlet of the air is happen there only, and the second one is the compression stroke, and the discharge or the delivery of the compressed air also happens in during the compression stroke. Okay, and also in the right figure you can see the indicator diagram, the simplified indicator diagram, by removing those pressure bumps that at point D and B. So this is the you know simpler indicator diagram. This is okay, and the work done, if we calculate the work done in this during this indicator diagram, we can calculate that by this formula, that W is equal to P2 Vc minus Vd. So the pressure at constant pressure P2, this at constant pressure P2, this pressure change, the volume changes from C to D, so work is done in that, plus the adiabatic, PV raised to power n is equal to constant, so adiabatic work done from point B to C, that component is this, and minus the during the suction stroke, the expansion of the gas in the clearance volume happens from D to A, so that is the negative work, that is this component shows that work only. And also from point A to B, that work is, this is also a negative work, because the air is getting sucked from high atmospheric pressure to the low cylinder pressure, so this is also the negative work. So the total work done during this cycle is the whole term. Okay. Also, as the in the case of reciprocating compression, there is this clearance volume there, and also the sweat volume is also there. So one more term here, the important term is the volumetric efficiency, and this volumetric efficiency is given by this formula, that is efficiency is equal to 1 plus c minus c into p2 by p1 raised to power 1 minus n. Here c is the compression ratio. Okay. So now from this formula, the volumetric efficiency formula, you can see here, if the pressure ratio P2 by P1, the value of pressure ratio is higher, that means this whole negative term will be higher, means the volumetric efficiency will be less. Okay. So higher pressure ratio means lower volumetric efficiency. Similarly, the higher the value of C, the higher the compression ratio. Also, this term is high. So, the volumetric efficiency decreases with increasing compression ratio or increasing, uh, not the compression ratio. So, basically, if the clearance volume is higher, if the clearance volume is higher, that means there is more gas for expansion and less air will be sucked into the cylinder. So the actual suction of the fresh air will be reduced if the clearance volume is higher, and that means the overall efficiency will decrease, or volumetric efficiency is also decrease in that case. So similarly, we can say the volumetric efficiency depends on clearance volume as well as the pressure ratio, and the volumetric efficiency decreases as we increase the clearance volume and pressure ratio. Okay. Yeah. So that's how this pressure ratio and clearance volume affect the volumetric efficiency of a reciprocating air compressor. Also, these air compressors are used in multiple stages to, to increase the pressure further. So if a if a reciprocating air compressor uses jet multiple steps or multiple stages, then the optimum pressure ratio at each stage is given as this Px by P1 is equal to P2 by P1 raised to power 1 by Z. Okay, so P2 is the final pressure and P1 is the initial pressure, and their power is 1 by Z. So basically, if it is a two-stage compressor, the pressure ratio uh, is the P2 by P1 raised to power 1 by 2, and for Z stages, it will be P2 by P1 raised to power 1 by Z. Okay. So this is the brief of the reciprocating air compressor, and based on this we will solve some questions. Okay. So let's move to the questions here. So the first previous year question for the NPTEL course, applied thermodynamics. So this question is which of the which of the following nature of the pumping characteristic is or are true for a reciprocating compressor. Okay. So the question is about reciprocating compressor, and what are the characteristics of a reciprocating compressor uh, with respect to these given options. Okay. So a reciprocating compressor characteristic. So in the case of reciprocating compressors, the intermittent flow, yes, the flow is always intermittent. Okay. And those those rotary and dynamic air compressors, in those cases the flow is continuous, but in the case of reciprocating compressor the flow is intermittent. Continuous flow, no. The positive displacement machines, yes, they are positive displacement machines. The compression happens because of the reducing, uh, reducing area. Okay, as the piston moves up, the area, the volume is reducing, and due to that reduction in the area or volume present, the compression happens. So that's why it is called as positive displacement machines. So for a reciprocating compressor, it is a reciprocating compressor, so it results in intermittent flow. So it the delivery of air is at every second stroke, and it is not continuous. Also the reciprocating compressors are positive displacement machine, that is also right. And these are the dynamic machines, so they are not dynamic machines. They do not transfer the kinetic energy to the gas or air for the compression purpose, but these machines use positive displacement for the compression work. So for the first question, that is all about the reciprocating compressor characteristic. So reciprocating compressor results in intermittent flow, and they are positive displacement machines, but they do not results in continuous flow, and they are not dynamic machines. Okay, so the option first and option third are the correct option. Okay, so it was very basic question. So let's move to the second one. So the second one is reciprocating air compressors handle high mass flow rates at high pressure ratio, low mass flow rates at low pressure ratio, high mass flow rate at low pressure ratio, low mass flow rates at high pressure ratio. Okay, so by the definition and their use, the reciprocating air compressors are basically used for low flow at high ratio, that we all saw in the the second slide, that the reciprocating air compressors work for low flow and high ratios, and for high flow and low ratios, for them there are rotary devices or these dynamic compressors or all those things. Okay, so the reciprocating air compressor handle the low flow and high ratio. So the high mass flow and high ratio, this is wrong. Low mass flow rate and low pressure ratio, no. Low, this is okay. So high mass flow rates at lower pressure ratio, this is also wrong. Lower mass flow rate at higher pressure ratio, this is the correct option. Okay, so a reciprocating air compressor handles low flow but at high ratios, high pressure ratios. Okay, this is the correct option. So let's move to the next one. So the next question is here is the thermodynamic nature of compression process in a reciprocating compressor. So the third question is the thermodynamic nature of compression process in a reciprocating compressor that incurs minimum power is. Okay, so here it is being asked is, so which one is the process of reciprocating compression that results in minimum power. Okay, so minimum power. So here are multiple processes. So the first is the isothermal process, second is adiabatic, isentropic and polytropic. So adiabatic, the reversible adiabatic process results in maximum compression work, as we saw in the second slide. Similarly, the polytropic process also result in some work, but that is not the minimum work. But the if the process is happening at isothermal, as an isothermal process, then the minimum work is transferred to the, or minimum work is done on the gas compression. Okay, so minimum work or minimum power is supplied in the case of isothermal process or isothermal compression. So here the question is the thermodynamic nature of compression process in the reciprocating compressor that incurs the minimum power is the isothermal process. Okay, so isothermal process means minimum work, reversible adiabatic process means maximum compression work, and the polytropic processes are in between isothermal and adiabatic processes. Okay, yeah. So the option 1 is the right option or right answer for this question. So let's move to the next one. So the next question here is, so the reciprocating air compressor is a positive displacement compressor. That is true, that we already talked about in the second slide. Reciprocating compressors are positive displacement compressor because the compression of air happen because of the reducing area or reducing volume of the space. Okay, so that's why it is called as positive displacement compressor. So reciprocating compressors are positive displacement compressor. So this statement is true. So let's move to the next one. Here is the next one. The effect of increase in clearance volume of a reciprocating air compressor is to increase the induced volume of the gas. Okay, so basically what happens is, if the clearance volume is more, if the clearance volume is more, then after the or at the end of the compression, when piston starts moving downward, in the downwards movement of the piston, the gas that is trapped in the clearance volume will start expanding, and as the clearance volume is higher here, means the more gas is present, more gas is present in the clearance volume means more expansion of the gas will be there. The more gas will be there for the expansion means there is less space for the fresh, fresh charge or fresh gas to come into the cylinder. That means if we increase the clearance volume, the the available or induced volume of the gas will be lower. Okay, so here the question is, the effect of increase in clearance volume of a reciprocating air compressor is to increase the induced volume of gas. So this statement is false. Why? Because as you increase the clearance volume, that means you are reducing the induced volume. Okay, so increasing in clearance volume, increase in clearance volume means induced volume is reducing. Okay, so clearance volume increasing, induced volume decreasing. So this statement is false. Increase in clearance volume doesn't result in increase in induced volume. Okay, that is the false statement. Let's move to the next one. So this next question is, the volumetric efficiency of a reciprocating air compressor decreases with increase in pressure ratio. Yeah, that is true, as the volumetric efficiency neta, yeah, so the volumetric efficiency neta is given by 1 plus C minus C P2 by P1 raised to power 1 by N. And now here, if we increase the pressure, so if we increase the pressure ratio P2 by P1, that means increasing the ratio P2 by P1 will result in increase in this whole term. Okay, and if we increase this whole term, the efficiency will decrease. Okay. So as it is given, the volumetric efficiency of reciprocating air compressor decreases with the increase in pressure ratio. So that statement is true. As you increase the pressure ratio P2 by P1, this will result in decrease in the volumetric efficiency. So this statement is true. Okay. So let's move to the next one. So the next question here is, in multi-stage compression, an intercooler is introduced between stages of compressors so that the gas will enter the second stage at same temperature at which it entered the first stage. Okay. So the question is saying, multi-stage compression, intercoolers are used. Okay. And when the gas enter into the second stage, it is the same temperature at which it enters the first stage. Okay. So basically, intercooler, what intercoolers does is, when we use the multi stage compressors, from this the outlet of the first compressor to the inlet of the second compressor, this is introduced, the intercoolers are introduced to reduce the temperature of this gas to the, again, to the atmospheric temperature. And then this is air compressed by the first stage is now fed or induced to the second stage at the same the same atmospheric temperature. Okay. So this statement is correct, because in the multi-stage compression with intercooler, the intercooler usually reduce the temperature to that atmospheric temperature, and the into the second stage the gas is at atmospheric temperature again. Okay. So this statement is correct. So yeah. So in the multiple or multi-stage compression, intercoolers are introduced between two stages, and they reduce the temperature from from outlet to the atmospheric temperature, and this statement is correct. Okay. So now let's move to the next question, and this next question here is, the actual power input to the compressor is smaller than the indicated power. Okay. So yeah, the actual power input to the compressor is smaller. So no, the actual power input to the compressor is higher than the indicated power, but not the, is smaller than the indicated power. Okay. So the indicator, apart from the indicated power, there are, you know the mechanical losses, the air leakage, the leakage through the walls, and all those things are, all those leakage and losses are there. Okay. So in actual, in the reality, the actual input to the compressor is higher compared to the indicator power, but not the smaller. Okay. So this statement is false. This actual power input is uh, you know is more than the indicated power, but not the smaller one. Okay. So this statement is false. So again, pretty simple and direct question from the concepts. So let's see the next one. So this next one is, a reciprocating compressor is there, receives air at mass flow rate of 5 kg per minute. Okay. And running at 320 revolutions per minute. Okay. The mass induced per cycle is. Okay. So as we know that reciprocating air compressors are two stroke are two-stroke machines. Two-stroke machines means the cycle completes in two-stroke, and two-stroke means 360-degree rotation. That means every cycle happens in one revolution of the shaft. Okay, so 320 revolutions means 320 cycles per minute, and also the mass flow rate m dot is also 5 kg per minute. Okay, so 5 kg gas is induced, the 5 kg of air is induced per minute for 320 cycles per minute. Okay, so 5 kg air is there for 320 cycle, so the air flow per cycle, the mass flow rate per cycle can be calculated as the 5 kg air for per minute and 320 cycle per minute. Okay, so that is 5 by 320, and if we calculate it, so we divide this 5 by 320, so that should be equal to 5 by 320 is 0.0156 kg per cycle. Okay, and what is being asked here is the mass in kg induced per cycle. So mass in kg induced per cycle is 0.015 kg per cycle, and that is the answer. Okay, yeah. So in this, for the given air compressor and the given mass flow rate of 5 kg per minute, for a compressor that is running at 320 revolutions per minute, the mass flow rate per cycle is 0.015 kg per cycle. Okay, so that is also a similar simple question. If you have any doubt, I think in the room is Manjeet Singh. If you have any doubt, you can ask, or we can move to the next question. Yeah. So the next and final
No,
question.
sir. No any doubt.
Yeah. So let's move to the next, the final question from this assignment. So a multi-stage compressor incorporates Z number of stages with perfect intercooling. Okay? With perfect intercooling between the stages. So a multi-stage compressor is this. Z number of stages are there. Intercooling is there. The compressor receives air at pressure P1 and delivers the compressed air at P2 for a minimum indicated power requirement. The pressure ratio PS is. So as we discussed in the second or third slide, that the minimum for a minimum indicated power requirement, the pressure ratio Px by P1 for the minimum indicated power requirement is P2 by P1 raised to power 1 by Z, where the Z is the number of stages. Okay, so that we discussed in the second or third slide already. So this is basically a simple question here is, we have this Z stages for perfect with the perfect intercooling, and the pressure ratio, the final pressure ratio is P2 by P1. So the stage pressure ratio PS can be given as P2 by P1 raised to power 1 by Z. So the option 1 is the power is Z, so this is wrong option. PS is P2 by P1 is 1 by Z, this is the right option. Again root Z, this is wrong, and 1 by Z root, this is also wrong. Okay, so the option B is the correct option. For a multi-stage compressor that has Z stages with perfect intercooling, the stage pressure ratio for minimum indicated power requirement will be P2 by P1 raised to power 1 by Z. Okay, so this is again a formula based question, and that the second option is the correct option here. Okay, so yeah, this is the correct option. So so this was the last question in this assignment, as well as in this series of live interactive sessions under the course of applied thermodynamics. So if you have any doubt till here from this chapter to the other 12 chapters, you can ask, uh, or we can close the session if you don't have any doubt. Okay, so I think no one has any doubt. So we are closing this session. So this was the last session in this live session series. So yeah, so we close the session and see you soon in the other courses. Yeah, we are closing the session.